Hello! Today Group 3 will be presenting on one of the most unique wireless networks on Earth, the Deep Space Network. The Deep Space Network, or DSN for short, allows us to communicate with spacecraft across our solar system and beyond. We believe that this network is one of the most challenging to implement due to its operation in an unusual environment like space. I'm sure many of you remember hearing about the Mars rover that touched down on February 18th. You may also be wondering how exactly we were able to communicate with these faraway spacecraft to send and receive information. The answer is the same way that we handle wireless data transmissions on Earth: radio waves traveling at the speed of light. So that leads us to this question. How long do you think it takes for a radio wave traveling at the speed of light to reach Mars? The answer might surprise you, so let's take a look. This video gives us a great visual representation of how long it takes. As Earth begins to zoom out, a radio wave pulse is emitted from our planet into space. An RF pulse will emit thereafter every 3.3 seconds. As we begin to zoom out even more and we can see our moon in the distance, we can see that it doesn't take very long to reach it, coming in at just about 2.5 seconds. Now we will zoom out even more so that the distance between Earth and Mars is in view. And for the sake of time for this presentation, I'm going to speed this up a little bit. But you can see the running time up here. So you can see even after I speed it up, it's still taking quite a bit of time. So that original green color in the front is our original RF signal, and it's traveling at 186,000 miles per second, which is the speed of light. And it takes 179 million miles to reach Mars, so it's quite a bit of time. So these distances and speeds are simply incomprehensible to us, but thanks to visual demonstrations like these, we can kind of begin to understand just how powerful this is. So now, as we begin our final approach to Mars, I'm going to slow it down again just so that you can see how long this really takes. Remember too that these data transmissions are half duplex, which means that they can communicate in both directions but not simultaneously. So now our original signal has just crossed Mars after 3 minutes and 2 seconds, with a round-trip time totaling just over 6 minutes. Despite the large delay, the transmissions of these signals are all supported thanks to the DSN, which leads us to our thesis. To support communication during interplanetary missions, the Deep Space Network and its terrestrial collection of highly capable antennas is crucial in ensuring that vital data is successfully delivered in such an unpredictable environment. After our presentation, we hope that you will understand the technical aspects surrounding the DSN, realize why the DSN is such an important part of our space missions, recognize the limitations and problems the DSN is faced with, and also consider future changes to the DSN to support upcoming missions.
Now we are going to discuss what the Deep Space Network is and how it came to be. The Deep Space Network utilizes a collection of highly capable antennas to wirelessly transmit signals millions of miles across the universe to communicate with interstellar spacecraft. The network was created by NASA's Jet Propulsion Laboratory, which belonged to the U.S. Army before being transferred to NASA in 1958 to help design a program to explore space with robotic spacecraft. The Deep Space Network is now one of our strongest links to the world beyond Earth. It's a key component in allowing us to communicate with satellite and spacecraft, providing us with pivotal insight into our solar system. The Deep Space Network is not unique to NASA. Other countries have developed their own versions of our Deep Space Network, including networks in China, India, and Japan. The DSN is able to exchange information with these other networks as they all follow the Consultative Committee for Space Data Systems standards. The DSN has an agreement with the European Space Agency's European Space Tracking Network to mitigate any coverage gaps in either network. This partnership has allowed both agencies to incur significantly lowered costs by sharing their resources and services. The agreement allows cross-support for tracking, space navigation, mission operations, and ground data system services. The partnership also allows both agencies to alleviate risks by offering backup ground stations during critical missions. Now we will explore the technicalities surrounding the Deep Space Network. The DSN has 3 ground stations that house the network's large antennas. They are located in Madrid, Spain, Canberra, Australia, and Barstow, California. The 3 stations are carefully placed in semi-mountainous, bowl-shaped regions to eliminate unwanted radio signal interference. The complexes have been placed exactly 120 degrees apart, which ensures that at least one complex is able to reach spacecraft as the Earth spins and spacecraft travel, leaving absolutely no room for coverage gaps at any point. Each complex contains one massive dish stretching to 70 meters, which is nearly the size of a football field. As communication began to expand past Earth's orbit, it was clear that a more sophisticated way of communicating was needed. This led to the creation of these large antennas. They are able to track spacecraft billions of miles from Earth. Essential to the seamless operation of the DSN is the size of the antenna's reflector. It must be within half an inch all the way across with absolutely no distortion. In addition, each complex has at least one 34-meter beam waveguide antenna and one 34-meter high-efficiency antenna. The beam waveguide antenna includes 5 additional precision radio frequency mirrors, which direct the signals to a room below ground. This protects the electronics from a potentially damaging and unpredictable climate. There are 3 of these beam antennas at the California complex, 2 in Spain, and 1 in Australia. Each complex also features a control room, which forwards data to the main Jet Propulsion Laboratory located in California. The JPL control room is manned by engineers every day of the week. A plaque located in the floor of the room declares the lab the center of the universe. Fun fact, there have been 4 marriage proposals in the so-called center of the universe. The JPL control room forwards all relevant data to researchers, engineers, and scientists throughout the globe.
Now we're going to dig into the technical aspects of how the DSN operates. Let's begin by looking at the antennas. In some of the previous pictures that were shown of the DSN, it's hard to miss the enormous circular dish. That is called the parabolic reflector, which is primarily responsible for efficiently capturing or directing the maximum amount of RF energy. The DSN and spacecraft also support both high and low gain antennas. As expected, high gain antennas are utilized more often by the DSN because more power is concentrated into the narrow beam. Let's take a look at how an RF signal is received by these antennas. During a downlink session, when information is being received by the ground stations, the RF signal is captured by the parabolic reflector and focused to the subreflector, which then focuses the energy to the antenna's base by bouncing it off solid or dichroic mirrors to separate the incoming frequency bands. When a signal is being sent from the ground stations, the same process occurs in the opposite direction, and utilizes a klystron that boosts the signal to output approximately 20 kilowatts of RF power. The DSN also utilizes a suite of unique networking protocols to successfully transmit RF signals. The TCP/IP protocol suite alone does not work very well in interstellar communication because of the unpredictable and unreliable nature of the environment. Instead, NASA developed a special protocol called the Delay or Disruption Tolerant Networking Protocol that is used when frequent disruptions and high error rates are exhibited. It is important to note that DTN is based on TCP/IP and follows many of its foundations. A network that communicates with spacecraft across our solar system must also be designed with timing and synchronization in mind. To determine an accurate position of a spacecraft, very stable atomic clocks are used at ground stations that only experience an average of 1 second deviation in 100 years of operation. Additionally, the comparison of 2 very geographically distant clocks relies on all-in-view GPS time transfer. Because a signal may experience a high amount of attenuation during transmission, spacecraft utilize forward error correction, like Reed-Solomon code and CCSDS turbo codes, to help alleviate problems. Security, of course, is another important factor, so a secure VPN is used to interconnect base stations, providing integrity of service when transmitting data.
All of the information that we've presented thus far begs the question, what is the point? Why do we need the DSN? The satellites, probes, and rovers navigating space are not completely autonomous. We must be able to communicate with spacecraft. The DSN allows us to connect to spacecraft and receive data from the depths of our solar system. We can instruct, trace, and check in on spacecraft thanks to the DSN. we are also afforded invaluable access to rare images of our planets and solar system. There are various types of data that the DSN allows us to transmit, including scientific information from spacecraft instruments, navigation measurements, commands to control objects, and photos and videos for closer missions. Beyond communicating with our man-made spacecraft, the DSN also has the potential to detect radio frequency signals from other galaxies. The Deep Space Network has allowed us to probe our solar system through a multitude of DSN-supported missions. The Voyager missions are only feasible thanks to the Deep Space Network. Both Voyager 1 and 2 were launched with the goal of reaching Jupiter and Saturn, before being extended to the unprecedented mission of reaching interstellar space. DSN allows us to communicate with both spacecraft and gauge critical information about the region. Earlier this year, NASA sent a probe to Voyager 2 and successfully received confirmation back that the signal was received. This was all made possible due to an upgraded dish at the Australian complex. The Juno mission sent the Juno spacecraft to Jupiter. To communicate with Juno, all of the antennas at the Australia site were used in tandem with those at the Goldstone location. This was the very first time that the DSN combined receiving power in the form of arrayed antennas. The New Horizons probe set out to do a flyby of Pluto in 2006. Thanks to the DSN, icy mountains were discovered on the planet, as well as a clear image of one of Pluto's moons. Perhaps the most well-known mission is Apollo 11. The images and video of Armstrong on the moon were able to be brought to people's television sets throughout the country due to the Deep Space Network. The Mars exploration rovers, Spirit and Opportunity, are able to roam the Red Planet and report their findings of the terrain, climate, and atmosphere back to the DSN. The rovers delivered panoramic images of Mars, as well as thousands of crisp images depicting the various rocks and soil to Earth. Just a few months ago, the Mars Perseverance rover arrived at the Big Red Planet. We are currently able to track its exact location on an interactive map and see raw images the rover takes of the planet. It also carried with it a helicopter, actually, that NASA plans on testing in the upcoming weeks. The consequence of the Deep Space Network cannot be overstated. As I have explained, the DSN has acquired essential information about the world beyond Earth that we really wouldn't have access to any other way. This quote from Neil Armstrong upon landing on the moon perfectly sums up just how important the Deep Space Network is. We really wouldn't have ever heard this iconic quote without it.
Now that we understand why the DSN is so important, let's examine some of its benefits and limitations. The DSN has many benefits, but there are a few that are most prominent. Built in a time where long-distance wireless communication was just at its inception, the DSN has stood the test of time, continually growing and advancing since the 1950s. There's a picture at the bottom of the slide that shows one of the 70-meter antennas from around 1966 that is still operational today. Another crucial benefit the DSN boasts is the scalability of the network. Throughout the many years, various additions have been made to the DSN without affecting the reliability of other antennas. The DSN is also interoperable with DSNs from other countries, culminating in an atmosphere that praises research and science behind interstellar exploration. Despite the many benefits of the DSN, success inevitably comes coupled with some drawbacks. The 70-meter antennas will eventually need to be decommissioned as newer, more advanced hardware is beginning to take over. This is due in part because of the immense operational costs that come with using this expensive equipment. According to NASA's DSN aperture fee algorithm, the estimated yearly cost of using the 70-meter antenna for 4 2-hour-long contacts per week is $3.43 million. Additionally, repairs on this equipment is timely, sometimes taking a few months or longer to complete. Finally, because all of the DSN ground stations are based on Earth, transmission rates to and from spacecraft are highly limited. There are some problems, however, that the DSN cannot solve due to the limitations of physics or other natural phenomena. Cosmic noise, which is similar to thermal noise, is one of those prominent threats. Because these waves must travel far distances, the loss of power in the signal is expected. The inverse square law states that the power of any signal falls with the square of the distance traveled. This means that the initial strength of the signal transmitted from Earth will be reduced significantly to reach a spacecraft. Communication with objects in space is also challenging because it's harder to maintain a connection with a rapidly moving object than a stationary one. A signal may also experience abnormal atmospheric conditions or pockets of ionized gas that affect transmission. The DSN does its best to work with these complications and is surprisingly successful at mitigating the various problems.
Now let's take a second and look ahead to the future. The deep space must mold to accommodate the growing magnitude of data being transmitted and received through the network. Many of DSN's antennas are already in the works to be upgraded because they're just falling short of the required performance standards. According to NASA, DSN must be able to support double the number of spacecraft and 100 times the downlink performance by the year 2030. Some key additions for a successful next-generation DSN include large arrays of small antennas, orbital data relays, and optical communication. Large arrays of small antennas would help reduce costs in the long run and also mitigate risks. Orbital data relays would allow for the DSN's reach to stretch even further, and optical communication would open the door to incredibly high data rate transmissions. The Deep Space Network has already started to upgrade. Deep Space Station 43 had hardware over 50 years old, and NASA recognized it was long past time for an upgrade. I briefly mentioned this antenna earlier because it is a single antenna capable of sending instructions to Voyager 2. Station 43 was not capable of this overnight. The dish has been offline for over a year. It returned in February with 2 new transmitters and upgrades all throughout. Earlier this year, a new antenna was added to the DSN's collection. Deep Space Station 56 is a 34-meter dish located at the Spain complex. It is dubbed the all-in-one antenna because it is capable of communicating with all DSN-supported missions. This is monumental because it can then serve as a backup dish for all of the antennas stationed at the Spain complex. The improvement to the Spain complex and the advancement of Station 56 is likely just a preview of what is going to come to the Deep Space Network. To conclude our look into the next generation of the Deep Space Network, I want to note some future developments that we can all look forward to. First of all, I think we can all agree that live video delivered by space lasers sounds pretty cool. NASA is currently developing Deep Space Station 23, which will be able to test the waters of optical communications, specifically deep space optical communication. Station 23 will have the required equipment to receive a laser from a spacecraft, and if all goes to plan, these lasers will allow data rates to skyrocket. The journey to space is anything but a safe one. Astronauts face a number of threats, including solar particles streaming from the sun. NASA's Sunrise aims to get a better idea of how these so-called space storms work. 6 spacecrafts will orbit the Earth and, through communication with the DSN, hopefully create a map of these bursts. This will help protect astronauts traveling through space by giving them a better idea of the environment that they're entering into. And lastly, I just want to mention the Ingenuity Mars helicopter once more. This past Monday, it actually made its first flight, and assuming that it was successful, it was the very first powered and controlled flight on another planet thanks to the instructions it received through the Deep Space Network.
Now to complete our presentation, Autumn and I have drawn a few conclusions worth noting. To begin, the Deep Space Network has successfully supported various missions for decades and has set a strong example for other countries to follow in creating their own DSNs. Because the DSN is highly scalable and interoperable with other ground stations, it has the potential to be the leading contender in space missions for years to come. The DSN has also circumvented many of the unique networking problems that exist in this environment in an innovative manner. However, future, more complex manned interplanetary missions will require the DSN to support higher transmission rates and lower latency. This may be achieved in future implementations thanks to optical technologies like lasers or arrays of antennas.
Now I'm going to showcase a game that NASA created that really exemplifies how complex of a system the Deep Space Network really is. So we're going to have this linked down below so you guys can all test it out and see it, just how difficult it is for yourselves. So The idea behind it is that this is our antenna and we just need to aim it and try and transmit and receive data. I'm not very good at it, and I'm also trying to talk, so give me some credit. But yeah, hopefully it shows that it's really difficult to aim all of these correctly, and it's obviously just astronomically more difficult in space and not on our little computer screens. So yeah, if you guys could all test it out, that would be great, and it just really bring home the point that this is a really impressive system.
Another great resource to further explore the Deep Space Network is the DSN Now website. This website gives us a live look at the DSN antennas in all 3 worldwide locations. We can see which antennas are currently operational and the kind of data that is being sent or received. This antenna, for example, seems to be receiving, downlink data from the Mars Odyssey. So you can look at all of these different antennas, and it changes periodically because this data is live. But this is a really interesting website if you're still interested in the DSN or would like to stay on top of the Mars 2021 mission. Finally, we would like to present you with our discussion questions. First, can you think of any further implementations of the DSN technology that may be untapped? Secondly, propose a solution that combats the problem of low transmission rates with the DSN. Finally, what do you think is the biggest threat to the success of the DSN? We would like to thank you very much for listening to our presentation, and we hope that you found this technology as interesting as we did. If you have any questions regarding our topic, please let us know in the discussion below. Here's a list of the sources we referenced.